Hello, my name is Yash Shalar, and this is my lab report on the motion of an object moving at a constant speed. In this experiment, I observed the motion of a skateboard moving 3 meters at a constant speed. The main purpose of this lab is to analyze the motion and develop a computational model that accurately describes the observed data based on Newton's second law, or the momentum principle. I'll also compare my model's predictions to the observed data and discuss the key physics principles involved. So the purpose of this lab is to understand and model the motion of an object moving at a constant speed, ensuring that this model aligns with the physical principles of Newton's second law. In this experiment, I use Newton's second law, which states that the net force on an object is equal to the mass of the object multiplied by its acceleration. Since the skateboard moves at a constant speed, the acceleration is 0, implying that the net force acting on the skateboard is also 0. This means the forces acting on the skateboard, such as friction and gravity, balance each other out. My computational model, the one that we had as a group for our lab, predicts that the skateboard will move at a constant velocity, and my observations support this prediction. And now here's the video and analysis, and I'll compare it to my model later. So this was the system, not the surroundings. So the system consists of the skateboard, while the surroundings include the surface it moves on, the air around it, and the gravitational field of the Earth. The interactions between the system and its surroundings are crucial, as they include gravity, friction, and the normal force, which together determine the skateboard's motion, as you can see in this video, which is just across these 3 meters. So the initial conditions for the experiment were as follows. The skateboard started from a rest position of 0 meters and was pushed to a constant speed before releasing it to travel the full 3 meters. The surface was flat and smooth, minimizing external forces such as friction that could affect the skateboard's velocity. These conditions were necessary to ensure that the skateboard maintained a constant speed throughout its entire motion. This is the video and then using the tracker software, I was able to analyze the motion and extracted the positions of skateboard at various times. These data points are plotted on a position versus time graph later. Here, I'll speed this up really quickly. But yeah, you can see I plotted all those points on the skateboard using the tracker software and all the way to the end. And then we get this position versus time graph shown here on the right. The observed data, shown as red points on the graph, indicate a linear relationship between position and time, confirming that the skateboard moves at a constant speed. And then here's my computational model. This is what I used to predict the skateboard's motion. The model assumes no net force acting on the skateboard, meaning it moves at a constant velocity. The predicted position versus time graph is shown on the left. This is the object. This is what the skateboard is supposed to be. It moves at a constant velocity here, and this is position versus time. As you can see, it's quite similar to the one we have here. Just straight up. And then we were to compare the predicted and observed data. When you compare them, you can see that both the predicted and observed graphs show a linear relationship, indicating the model accurately predicts the skateboard's motion. The model's prediction and the observed data closely align, verifying the accuracy of our model. The main assumption in this model is that the net force on the skateboard is 0. This assumption holds because in reality, any forces acting on the skateboard, such as friction and gravity, basically cancel each other out, resulting in no net acceleration. Therefore, the skateboard moves at a constant velocity, which is consistent with the observed data. What if you flip the axes in our analysis, though? So if we did flip them, if you interchange the positive x and negative x directions, the slope of the position time graph would be negative instead of positive, but the magnitude of the slope, which corresponds to velocity, would remain the same. This means that the skateboard speed remains constant, but the direction of the motion would be reversed in analysis. So the velocity and the speed would remain the same, just in the opposite direction, and the motion will also be in the opposite direction. And then next, what does it mean, net force and forces involved? So this question was asked in the instructions about the net forces acting on the skateboard and whether they cancel out. So the fact that our model accurately predicts the skateboard's motion when the net force is set to 0 suggests that multiple forces are acting on the skateboard but cancel each other out. These could include friction, normal force, and gravity. While we can't specify the exact number of forces, we know that they add up to 0 net force, resulting in no acceleration and a constant velocity. So there could be some source of error. Possible sources of error in this experiment could include inaccuracies in the video analysis or assumptions made in the computational model. For instance, if there was a slight incline or if the friction was not perfectly uniform, these factors could slightly affect the skateboard's motion. So I think this lab demonstrates clear understanding of Newton's second law and the conditions under which an object will move at a constant speed. The experiment, computational model, and analysis all align to support the conclusion that when the net force is 0, the object continues to move at a constant velocity. So in summary, this lab successfully demonstrated the principles of constant velocity motion through both observation and computational modeling, and the alignment between the observed data and the model supports the application of Newton's second law in this scenario, the skateboard model that we created as a lab. Thank you for watching, and see you next time.